There are moments, usually late at night, when time becomes noticeable. Not because it speeds up or slows down, but because everything else grows quiet enough for you to feel it. The room is still. The world outside has settled. And in that silence, you become aware of something moving through you. Something steady. Something unstoppable. You feel it in the rhythm of your breathing, in the slow drift of thoughts, in the simple fact that this moment is already slipping into the past as soon as you notice it. That movement is time. From the moment you wake in the morning to the moment sleep takes you again, time carries you forward, always forward. It moves you through conversations and meals and memories, through seasons and years, through changes so gradual you rarely notice them until they are already complete. Hair turns grey, faces change, buildings weather, shorelines retreat, photographs fade. Time moves, whether you pay attention to it or not. For your entire life, time has behaved in one very specific way. The past feels fixed. The future feels open. You remember yesterday, but you cannot revisit it. You can imagine tomorrow, but you cannot experience it yet. This one-way flow feels so fundamental that it hardly seems worth questioning. It feels like a law of reality itself. And yet, physics tells us something strange. The steady, universal time you experience each day is not quite what the universe is actually using. At the deepest level, time is not a single, rigid river carrying everything along at the same pace. It is flexible. It stretches, it bends, it responds to motion and gravity in ways that defy intuition. And under certain conditions, it behaves very differently from the time you experience in your daily life. This is not speculation. It is not metaphor. It is the result of a century of careful measurement, observation, and experiment. Clocks do not tick at the same rate everywhere. A clock on a satellite moves through time slightly faster than a clock on Earth's surface. A clock on a fast-moving spacecraft would age more slowly than one left behind. A clock near a massive object experiences time differently than one far away from gravity's pull. These effects are small in everyday life, but they are real. They are measurable. And they are built into the technology you already rely on. Without correcting for time dilation, GPS satellites would drift out of sync within hours. Your phone would not know where you are. Time, it turns out, is part of the structure of the universe itself, woven together with space into a single fabric called spacetime. And once you accept that, a deeper question begins to emerge. If time can stretch and slow and behave differently depending on conditions, is it truly impossible to move through it in other ways? This is where imagination usually takes over. Stories of machines and portals, of travelers stepping into the past or leaping into distant futures. Science fiction has explored these ideas for more than a century, often with little regard for whether such journeys could ever be physically possible. But beneath the fiction lies a serious scientific question. Not, can we build a time machine tomorrow? But does the universe forbid time travel at all? Surprisingly, the answer is not an immediate no. The same equations that describe gravity, black holes, and the expansion of the universe also allow solutions where time behaves in deeply unfamiliar ways. Solutions where paths through space-time curve back on themselves. Where cause and effect become tangled. Where the neat separation between past, present, and future begins to blur. Physicists did not set out to invent these ideas. They emerged naturally from the mathematics, and once they appeared, they could not be ignored. This does not mean time travel is easy. It does not mean it is practical. And it certainly does not mean it is safe. In many cases, the conditions required are so extreme that they may never exist outside theory. But the fact that the laws of physics do not automatically forbid such possibilities is profoundly unsettling, because it forces us to confront something deeper. Why does time feel as though it moves in only one direction? Why does the past feel locked while the future remains open? And if the laws of physics are largely time-symmetric, meaning they work the same forward and backward, why does your experience of time feel so irreversible? These are not philosophical curiosities. They are questions about the fundamental structure of reality, about entropy and memory, about why broken things do not reassemble themselves, about why you can remember yesterday but not tomorrow. You are already a traveler through time. Every second you move forward at the same steady rate, carried along by the universe itself. But that familiar journey may not be the only one permitted by the laws of nature. To understand whether time travel could ever be possible, and what that would actually mean, we first need to understand what time truly is. Not as a number on a clock, not as a line on a calendar, but as a physical dimension shaped by motion, energy, and the deep structure of space-time itself. And once we begin that journey, the universe becomes far stranger than the ticking of a clock would ever suggest. For most of human history, the answer seemed obvious. Time was simply there. It flowed like an invisible current beneath all events, measuring out the duration of things, providing the stage upon which everything happened. It was as fundamental as space itself, perhaps more so. You could imagine a universe without certain objects, without particular stars or planets, but it seemed impossible to imagine a universe without time. This was the view that Isaac Newton made precise in the 17th century. In his great work on the mathematical principles of natural philosophy, Newton described time as absolute, true, and mathematical. It flowed equably, he wrote, without relation to anything external. This meant that time existed independently of the things within it. Whether or not anything happened, whether or not anyone observed it, time simply passed at its steady rate, the same everywhere, the same for everyone. This conception felt right. It matched human experience perfectly. When you and a friend synchronize your watches and then part ways, you expect those watches to agree when you meet again. Time in Newton's universe was a universal metronome, beating out the same rhythm for a farmer in a field and an astronomer at a telescope, for a ship at sea and a philosopher in contemplation. It was democracy applied to existence itself. Everyone received the same time, measured in the same way. For more than 2 centuries, this absolute time served physics magnificently. It allowed Newton and those who followed him to describe the motions of planets, the fall of objects, the flow of rivers, and the orbits of moons with extraordinary precision. Predictions made using Newtonian physics proved accurate again and again. Bridges were built, machines were engineered, and eventually humans began to harness forces that would have seemed magical to earlier generations. All of this rested on the assumption that time was exactly what it appeared to be. But what is time really? This question haunted philosophers long before Newton and continues to puzzle thinkers today. Is time something that exists out there in the world, independent of human minds? Or is it merely a way we organize our experience of change, a mental framework we impose on the flow of events? Consider what time actually measures. When you look at a clock, you are watching a mechanism that counts regular intervals. A pendulum swings, a crystal vibrates, an atom oscillates between energy states. These repetitive motions are compared to other events, and from this comparison we derive our sense of duration. But are we measuring something real, or simply comparing one process to another. There is also the deep mystery of time's direction. We remember yesterday, but not tomorrow. We see causes precede effects, never the reverse. Eggs fall from tables and break, but broken eggs never reassemble and leap back onto tables. This asymmetry, this one-way character of time, is so fundamental to experience that we rarely question it. Yet the basic equations that describe how particles move and interact make no distinction between past and future. They work equally well in either direction. Why then does time seem to flow only one way? Part of the answer may lie in a concept from thermodynamics, the science of heat and energy. There is a quantity called entropy, which loosely describes the amount of disorder in a system. The second law of thermodynamics tells us that in any isolated system, entropy tends to increase over time. Things move from ordered states to disordered ones. Ice melts in warm rooms. Perfume diffuses through still air. Mountains erode into sand. This tendency toward disorder gives time its arrow. The past is the direction of lower entropy, the future the direction of higher entropy. We remember the past because our memories are physical records, ordered arrangements of matter that reflect earlier states of lower disorder. We cannot remember the future because those ordered records do not yet exist. But even this explanation raises further questions. Why was entropy lower in the past? Why did the universe begin in such an ordered state that it could spend billions of years becoming more disordered? These are questions that touch the very origins of the cosmos, questions we are still working to answer. For centuries, these puzzles remained philosophical curiosities. Time flowed, clocks ticked, and physics proceeded on its Newtonian path. But in the late 19th century, cracks began to appear in the foundations. Experiments with light produced results that did not fit the classical picture. Scientists studying electricity and magnetism found that their equations implied something strange about the speed at which light travels. Light, it seemed, moved at a fixed velocity. This in itself was not surprising. What was surprising was that this velocity appeared to be the same for all observers, regardless of how they themselves were moving. If you were stationary, light passed you at a certain speed. If you were moving toward the light source at tremendous velocity, you would expect light to approach you faster. But it did not. Light still passed you at exactly the same speed. This constancy was troubling. It did not fit with the simple addition of velocities that worked for everything else. If you walk forward on a moving train, your speed relative to the ground is the train's speed plus your walking speed. But light refused to follow this rule. Its speed remained unchanged, as though the motion of the observer simply did not matter. Something in the classical picture had to be wrong. Either the understanding of how velocities combined was mistaken, or the understanding of space and time themselves needed revision. The edifice that Newton had built, the absolute time that had served so well, was about to face a challenge that would transform physics forever. These cracks in the classical view would lead a young patent clerk in Switzerland to reimagine time entirely. And in doing so, he would reveal that time travel is not merely fantasy, but a consequence of the universe's deepest structure. His name was Albert Einstein, and in 1905, working in a patent office in Bern, he published a paper that would forever change our understanding of reality. He was 26 years old, unknown in the scientific world, spending his days evaluating technical applications, while his mind wandered through the deepest questions of physics. What he produced that year was not merely a correction to existing theory. It was a complete reimagining of space and time themselves. Einstein began with a simple premise. The speed of light is constant for all observers, regardless of their motion. This was the stubborn experimental fact that refused to fit the classical framework. Rather than dismiss it or explain it away, Einstein took it seriously. He asked what the universe would have to be like for this fact to be true. The answer required abandoning something that had seemed beyond question. If the speed of light is truly constant, then time cannot be absolute. Consider what it means to measure the speed of anything. Speed is distance divided by time. If two observers moving relative to each other both measure the same speed for a beam of light, but they disagree about distances because of their relative motion, then they must also disagree about time. There is no other way for the mathematics to work. Time itself must be different for different observers. This was the revolutionary insight at the heart of special relativity. Time is not a universal backdrop against which events unfold identically for everyone. Time is personal. It depends on how you are moving through space. Two observers in relative motion will measure different durations between the same pair of events, and both measurements will be correct. This effect is called time dilation, and it sounds impossible until you understand its necessity. Imagine two clocks, identical in every way, perfectly synchronized. One remains stationary, while the other is placed aboard a vessel moving at tremendous speed. When the moving clock returns to its starting point, it will show that less time has passed than the stationary clock. The moving clock is not broken. It has not malfunctioned. Time itself has passed more slowly for that clock because of its motion through space. At the velocities we encounter in daily life, this effect is vanishingly small. Walking across a room, driving along a highway, even flying in an aircraft. The difference in the passage of time is so tiny that it would take years to accumulate even a fraction of a second. This is why Newton's absolute time works perfectly well for everyday purposes. The speeds involved are simply too slow for time dilation to matter. But as velocity increases, the effect grows. At 10% of light speed, time aboard a moving vessel passes about 0.5% slower than for a stationary observer. At 90% of light speed, time slows to less than half its normal rate. At 99% of light speed, time moves at barely 1/7 its usual pace. And as velocity approaches the speed of light itself, time slows toward a standstill. This is not illusion. It is not a trick of perception or a limitation of measuring instruments. Time genuinely passes at different rates depending on relative motion. The universe is constructed in such a way that this must be true, and experiments have confirmed it beyond reasonable doubt. In the 1970s, scientists placed extraordinarily precise atomic clocks aboard aircraft and flew them around the world. When compared to identical clocks that remained on the ground, the airborne clocks showed slightly less elapsed time, exactly as Einstein's equations predicted. The difference was measured in billionths of a second, but it was there. It was real. The clocks in motion had experienced less time. More dramatically, particles called muons provided early confirmation of time dilation. These particles are created high in Earth's atmosphere when cosmic rays strike air molecules. Muons are unstable. They decay within millionths of a second. Given their short lifespan and the distance they must travel to reach Earth's surface, most muons should decay before arriving. Yet they reach the ground in far greater numbers than expected. The explanation is time dilation. Moving at nearly the speed of light, the muons experience time so slowly that their brief existence stretches long enough for them to complete the journey. What does this mean for time travel? It means that traveling forward in time is not fantasy. It is physics. If you were to board a vessel capable of traveling at a significant fraction of light speed, journey outward for what felt to you like a few years, and then return to Earth, you would find that decades or even centuries had passed in your absence. You would have leapt into the future, not through any mystical mechanism, but simply by moving fast enough to experience time more slowly than those you left behind. The satellites that enable global positioning systems account for relativistic effects in their calculations. Without corrections for time dilation, the navigation systems that guide ships and aircraft, and even the device in your pocket, would drift out of accuracy within hours. Every time you use such a system, you are relying on physics that confirms time does not pass uniformly for all things. This was Einstein's gift to our understanding of reality. Time is not fixed. It is elastic, stretching and compressing depending on motion through space. The faster you move, the slower your clock ticks, relative to those at rest. And while the speeds required for dramatic effects are far beyond current technology, the principle is established. The universe permits forward time travel as a natural consequence of its structure. But Einstein's revolution did not end with motion. When he turned his attention to gravity, he discovered that mass itself warps the fabric of time, opening even stranger possibilities. 10 years after his first revolution, Einstein produced another. In 1915, he completed his general theory of relativity, a framework so profound that physicists still marvel at its elegance more than a century later. Where special relativity had revealed that motion affects the passage of time, general relativity went further. It showed that gravity itself reaches into the fabric of time and bends it. To understand this, we must first abandon a familiar way of thinking. In Newton's universe, space was a fixed stage and time was a universal clock. Objects moved through this unchanging backdrop, attracted to one another by a mysterious force called gravity. Newton could describe this force with extraordinary precision, but he could not explain what it actually was. How did the sun reach across millions of miles of empty space to hold the Earth in orbit? Newton had no answer. He simply noted that the mathematics worked. Einstein provided the explanation. Gravity is not a force reaching across space. Gravity is the shape of space itself. More precisely, gravity is the curvature of space-time, the unified fabric in which both distance and duration are woven together. Imagine a stretched sheet of rubber, pulled tight and flat. Now place a heavy ball in the center. The sheet curves downward around the ball, creating a depression. If you roll a smaller ball across the sheet, it will not travel in a straight line. It will curve toward the heavy ball, following the contour of the distorted surface. This is gravity. Mass tells space-time how to curve, and curved space-time tells objects how to move. But here is the remarkable part. It is not only space that curves around massive objects, time curves as well. The presence of mass slows the passage of time in its vicinity. The stronger the gravitational field, the more slowly time passes. This is gravitational time dilation, and like its velocity-based counterpart, it is not speculation. It is measured fact. Consider the simple difference between a valley and a mountaintop. In the valley, you are closer to the center of Earth. Gravity is very slightly stronger there than at the summit of a mountain. According to general relativity, time should pass very slightly slower in the valley than on the peak. The difference is extraordinarily small. Over an entire human lifetime, it amounts to mere fractions of a second. But with atomic clocks precise enough to detect such tiny variations, the effect has been confirmed. Time genuinely passes faster at higher altitudes. This is why the satellites of global positioning systems require two separate corrections. They must account for time dilation due to their orbital velocity, which slows their clocks. But they must also account for their distance from Earth's center, which means they experience weaker gravity and therefore faster time. Without both corrections applied, the system would rapidly become useless. Now, imagine scaling this effect upward. Earth's gravity is modest by cosmic standards. But there are objects in the universe where gravity becomes so intense that time dilation reaches extraordinary proportions. Neutron stars are the collapsed remnants of massive suns. They pack roughly the mass of our star into a sphere only a dozen miles across. The gravity at their surface is so fierce that time there passes measurably slower than time far away. For every hour that elapses on a neutron star's surface, slightly more than an hour passes in distant space. The difference is small but significant, a consequence of gravity's grip on time itself. And then there are black holes. A black hole is what remains when a truly massive star exhausts its fuel and collapses under its own weight. The collapse continues without limit, crushing matter into a point of infinite density. Around this point lies a boundary called the event horizon. Once anything crosses this threshold, it can never return. Not light, not matter, not information of any kind. The gravitational pull within the event horizon is absolute. Near this boundary, time dilation becomes extreme. As an observer approaches the event horizon, time for them slows relative to a distant watcher. From far away, you would see the approaching traveler move more and more slowly, their motions stretching out, their clock ticking ever more sluggishly. At the horizon itself, time for the traveler appears to stop entirely from the distant perspective. They would seem frozen at the edge of the abyss forever. From the traveler's own point of view, the experience would be different. They would cross the horizon in finite time by their own clock, perhaps noticing nothing unusual at the moment of crossing. But while mere hours passed for them during their approach, years or centuries or even millennia might pass in the universe beyond. They would be traveling into the future simply by lingering near the most extreme curvature of space-time. This is forward time travel of the most dramatic kind, not through velocity, but through gravity. The deeper you descend into a gravitational well, the more slowly your clock ticks relative to the cosmos. Approaching a black hole and then somehow escaping, if such a thing were possible, would catapult you into the far future of the universe. We have now seen two mechanisms by which forward time travel is not merely possible but confirmed by experiment. High velocity slows time. Strong gravity slows time. The universe genuinely permits journeys into the future. Journeys that are already being made in tiny increments by astronauts in orbit and particles in accelerators. But there remains a far more troubling question. All of this is forward time travel, moving into the future more slowly than others. What about the other direction? What about traveling into the past? To ask whether time can run backward, we must venture into the strangest prediction of Einstein's equations, regions of space-time so twisted that past and future become tangled together. Traveling forward through time is strange enough. But the equations of general relativity permit something stranger still. Within their mathematical structure lie solutions that describe paths through space-time which loop back upon themselves. Journeys that end before they begin. Trajectories that return a traveler to their own past. These are not errors in the mathematics. They are not signs that the theory is broken. They emerge naturally from Einstein's framework, as valid as any other solution. Whether the universe actually permits such paths to exist is another question entirely. But the fact that they appear in our best theory of gravity demands that we take them seriously. The most famous of these theoretical structures is the wormhole. Imagine space-time not as a flat sheet, but as a vast, flexible membrane that can fold and curve in ways beyond ordinary perception. Now imagine that this membrane folds so dramatically that two distant regions come to touch. A tunnel might form between them, a shortcut through the fabric of reality itself. This is a wormhole, a bridge connecting points that would otherwise be separated by enormous distances. The concept emerged shortly after Einstein published general relativity. He worked with physicist Nathan Rosen to explore solutions that described such bridges, and for a time, they were called Einstein-Rosen bridges. The mathematics was sound. Two black holes, one in each of two distant regions, could theoretically share a throat connecting their interiors. Space-time itself would provide the passage. But these early wormholes had a problem. They were not stable. The throat would open and collapse so quickly that nothing could pass through. Not light, not matter, not even a signal. They were mathematical curiosities, not practical passages. Later work suggested a possible remedy. If a wormhole could be threaded with something called exotic matter, matter with negative energy density, the throat might be held open long enough for a traveler to pass through. Exotic matter sounds like science fiction, and in many ways it is. We have never encountered such substance in any quantity. Yet quantum mechanics hints that it might exist in subtle forms. The vacuum of space itself fluctuates with tiny amounts of negative energy under certain conditions. Whether this could ever be harnessed to stabilize a wormhole remains deeply uncertain. What makes wormholes relevant to time travel is a remarkable possibility. If one mouth of a wormhole could be moved at high velocity, while the other remained stationary, time dilation would cause the moving mouth to age more slowly. The two ends of the tunnel would then connect not just different places, but different times. Enter one mouth and emerge from the other in what would be, from a certain perspective, the past. This is speculative in the extreme. We have never observed a wormhole. We have no evidence that traversable wormholes can exist. But the mathematics permits them, and that permission is significant. It tells us that general relativity does not automatically forbid travel to the past. Wormholes are not the only structures that suggest such possibilities. In 1949, mathematician Kurt Gödel discovered a solution to Einstein's equations describing a rotating universe. In Gödel's cosmos, the rotation of matter drags space-time along with it in such a way that closed loops through time become possible. A traveler moving in certain directions could, in principle, return to their own starting point, not just in space, but in time. Gödel's universe does not match our own. Observations show that the cosmos is expanding, not rotating in the manner his solution requires. But the existence of his solution demonstrated something important. General relativity permits closed, time-like curves. Paths through space-time that loop back upon themselves are not automatically excluded by the theory. Another possibility involves rotating black holes. Unlike the simple, non-rotating black holes first described by Carl Schwarzschild, real black holes are expected to spin. A rotating black hole is described by what are called the Kerr solutions, named after the physicist Roy Kerr, who discovered them in the 1960s. The interior geometry of a Kerr black hole is far more complex than its non-rotating counterpart. It contains ring-shaped singularities and regions where the direction of time becomes scrambled. Some calculations suggest that a traveler falling through a rotating black hole might, under precisely the right conditions, emerge in another place and time, perhaps even in the past. The journey would be extraordinarily dangerous. The tidal forces near a black hole would stretch and compress any ordinary object beyond recognition, and it remains unclear whether the theoretical interior geometry of a Kerr black hole reflects what actually exists inside such objects. The mathematics is valid, but physics at such extremes may involve processes we do not yet understand. What all these scenarios share is a common feature. They are mathematical possibilities within general relativity that describe travel to the past. They are not observed phenomena. They are not engineering blueprints. They are solutions to equations, explorations of what the mathematics permits, rather than confirmations of what the universe allows. There is a vast gulf between a solution on paper and a structure in reality. Many things that are mathematically consistent turn out to be physically impossible. The laws of physics may contain deeper principles we have not yet fully grasped, that prevent these exotic structures from forming. Or they may not. We simply do not know. What we do know is that any form of backward time travel raises profound questions that go beyond engineering challenges. If the past can be visited, what prevents a traveler from changing it? What happens to cause and effect if effects can precede their causes? What becomes of logic itself in a universe where time loops back upon itself? Even if the mathematics permits such passages through time, the universe may have deeper rules that forbid their use. Laws that protect causality itself from unraveling. The moment we consider traveling into the past, we encounter problems that go beyond physics. We find ourselves tangled in questions of logic itself. If you could return to yesterday, could you change what happened? And if you changed what happened, what would become of the present from which you departed? This is the territory of paradox. And paradoxes have haunted the idea of backward time travel since humans first began to think seriously about it. The most famous is often called the grandfather paradox. Imagine a traveler who journeys into the past and, through some action, prevents their own grandfather from meeting their grandmother. If the grandparents never meet, the traveler's parent is never born. If the parent is never born, the traveler is never born. But if the traveler is never born, they cannot journey into the past to prevent the meeting, which means the grandparents do meet, the traveler is born, and travels back to prevent the meeting. The logic spirals without resolution. This is not merely a puzzle for philosophers. It strikes at the foundation of cause and effect. Our entire understanding of the universe rests on the principle that causes precede effects. You strike a match, and then it ignites. You drop a stone, and then it falls. This ordering of events is so fundamental that we rarely even notice it. But backward time travel threatens to unravel this chain. If an effect can precede its cause, what remains of causality? There are other paradoxes too. Consider what is sometimes called the bootstrap paradox, or a causal loop. Imagine a traveler who goes back in time carrying a book. They give the book to a young author who reads it and later publishes it under their own name. The traveler in the future obtains a copy of this published book and carries it back in time. Where did the book come from? Who wrote it? The information in its pages has no origin. It exists only because it exists, looping endlessly through time without ever being created. Such scenarios offend our sense of how things should work. Information, objects, even people might exist without any point of origin. They would be uncaused causes, violations of the logic that holds reality together. Some physicists believe the universe simply does not permit such violations. Stephen Hawking proposed what he called the chronology protection conjecture. He suggested that the laws of physics conspire to prevent time travel to the past. Whenever conditions approach those that would allow a closed time-like curve to form, some physical mechanism intervenes to stop it. One possible mechanism involves quantum effects. At the scales where wormholes or other time-bending structures might form, the quantum vacuum is not empty. It seethes with tiny fluctuations, particles and antiparticles, appearing and vanishing in a constant froth of activity. Near the threshold of a forming time machine, these fluctuations might amplify without limit. The energy density would grow so extreme that the structure would be destroyed before it could ever be used. This is not proven. It remains a conjecture, a well-motivated guess about how the universe might protect itself from paradox. But it suggests that the mathematics permitting backward time travel might be overruled by physics at a deeper level. Others have proposed different resolutions. The physicist Igor Novikov suggested what is called the self-consistency principle. Perhaps the universe does permit travel to the past, but only in ways that are self-consistent. Any action a traveler takes in the past must be compatible with the future they came from. You could attend events that already happened, witness moments from history, but you could never change them. The universe would somehow constrain your actions, making alterations impossible. In this view, paradoxes do not arise because they cannot arise. Only self-consistent histories are physically possible. A traveler might try to prevent their grandparents from meeting, but something would always intervene. A missed train, a wrong turn, an unforeseen obstacle. The universe would enforce its own consistency. This idea has a certain elegance, but it raises troubling questions about free will. If your actions in the past are constrained to be compatible with a fixed future, are you truly free to choose? Or are you merely acting out a script that was always written? There is another possibility, one that emerges from quantum mechanics. Some interpretations of quantum theory suggest that reality is not a single thread, but a vast, branching tree. Every quantum event splits the universe into multiple versions, each realizing a different outcome. In this many worlds picture, backward time travel might not create paradoxes at all. Instead, it might create branches. A traveler who prevents their grandparents from meeting does not erase their own existence. They simply moves onto a different branch of reality, one in which they were never born. The original timeline continues undisturbed. The traveler now exists in a new timeline, one they have created by their actions. No paradox occurs because there is no single, unified history to contradict. This is speculative even by the standards of theoretical physics. We have no direct evidence for the many worlds interpretation and no way to test whether branching timelines actually exist. But it offers a logical framework in which backward time travel might be possible without the contradictions that seem to make it impossible. What all these proposals share is a recognition that backward time travel, if it exists, must somehow avoid destroying the logical structure of the universe. Whether through physical mechanisms that prevent time machines from forming, constraints that enforce self-consistency, or branching realities that sidestep paradox entirely, the cosmos would need some way to protect itself. We do not yet know which, if any, of these resolutions is correct. The paradoxes remain unresolved, the questions open. Whether or not the universe permits journeys into the past, there remains a question closer to our present moment. What would it actually take to travel meaningfully through time, even into the future? we have seen that forward time travel is not merely possible, but proven. Moving clocks run slowly. Gravity bends the passage of duration. These are facts established by experiment, confirmed by the technology that guides aircraft and synchronizes communication networks. Yet there is a vast difference between the tiny fractions of a second accumulated by satellites in orbit and the dramatic leaps through time that capture human imagination. To travel meaningfully into the future, to skip years or decades or centuries while the world ages around you, requires conditions far beyond anything we can currently achieve. The physics is sound. The engineering is another matter entirely. Consider first the path of velocity. Special relativity tells us that the faster you move, the more slowly time passes for you relative to those at rest. To experience significant time dilation, you must travel at a substantial fraction of the speed of light. At half the speed of light, time slows by about 15%. Noticeable but not dramatic. At 90% of light speed, the effect becomes profound. A journey that takes 10 years by your own clock might see 20 years pass on Earth. At 99%, the ratio grows more extreme still. But reaching such velocities presents challenges that border on the insurmountable with current technology. The fastest objects ever launched by humanity are space probes, and even these travel at mere thousandths of a percent of light speed. The energy required to accelerate a meaningful payload grows enormously as velocity increases. This is not a simple linear relationship. As you approach light speed, the energy requirement climbs toward infinity. The mass of the accelerating object effectively increases from the perspective of an outside observer, demanding ever more thrust for ever smaller gains in speed. The rocket equation, which governs all propulsion based on throwing mass backward to push a vehicle forward, imposes brutal constraints. To reach even a tenth of light speed using chemical rockets, you would need a fuel mass so enormous that no practical vehicle could carry it. The numbers quickly become absurd. Mountains of fuel for grams of payload. More advanced propulsion concepts offer marginal improvements. Nuclear pulse propulsion using controlled explosions to push a spacecraft forward could theoretically achieve a few percent of light speed. Antimatter engines, which extract energy from the annihilation of matter and antimatter, offer the highest energy density known to physics. But antimatter is extraordinarily difficult to produce and store. The total amount ever created by all particle accelerators on Earth amounts to mere billionths of a gram. Accumulating enough to power an interstellar journey would require resources beyond anything currently imaginable. Light sails offer another approach. A vast thin sail could be pushed by intense laser beams to significant fractions of light speed. Such a vessel would carry no fuel, receiving its propulsion from installations that remain behind. Theoretical studies suggest that small probes might eventually be accelerated to perhaps 20% of light speed using this method. But scaling such technology to carry human passengers, along with the life support systems they would require, remains firmly in the realm of speculation. Even if propulsion could be solved, the journey itself presents difficulties. At high velocities, collisions with even tiny particles of dust become catastrophic. A grain of sand striking a spacecraft at 90% of light speed releases energy comparable to an explosion. Shielding against such impacts adds mass, which demands more energy for acceleration, which requires more fuel or larger propulsion systems. Each solution creates new problems, and then there are the biological considerations. Human bodies evolved for the conditions of Earth, not for years or decades, sealed in a metal container hurtling through the void. Radiation exposure, muscle deterioration, bone loss, psychological strain, the effects of long-term isolation. All of these would need to be addressed for any journey long enough to produce meaningful time dilation. What about the gravitational approach? Rather than accelerating to extreme velocities, a traveler might venture close to a massive object and let gravity slow their time. A black hole would serve this purpose admirably. Orbiting just outside the event horizon of a sufficiently large black hole, time could pass at a crawl while centuries accumulated in the universe beyond. But reaching a black hole presents its own challenges. The nearest known black hole lies thousands of light years away. Journeying there with current technology would take longer than human civilization has existed. And approaching closely enough to experience significant time dilation without falling irretrievably past the event horizon would require navigational precision beyond any current capability. There is also the Alcubierre concept. In the 1990s, physicist Miguel Alcubierre proposed a theoretical drive that would contract space in front of a vessel while expanding it behind. The ship itself would remain stationary within a bubble of flat space-time, while the bubble moved through the surrounding space at effectively unlimited speed. To an outside observer, the vessel would appear to travel faster than light without actually violating relativity's prohibition. But the Alcubierre drive requires exotic matter with negative energy density, the same elusive substance needed to stabilize wormholes. The amounts required are staggering. Early calculations suggested energy equivalent to the mass of an entire planet. Later refinements reduced this, but the quantities remain far beyond any foreseeable technology, and it remains unclear whether such matter can exist in the configurations the drive would require. We are left with a sobering assessment. Forward time travel is real, but dramatic forward time travel remains beyond our grasp. The physics permits it, the engineering forbids it, at least for now. Yet, this is not cause for despair. The history of technology teaches humility. Much that seemed impossible to one generation became routine for the next. The gap between theory and practice has been closed before. Perhaps the deepest question is not whether time travel is possible, but what its possibility or impossibility reveals about the nature of existence itself. We have traveled far in our exploration, from the steady flow of everyday time to the strange elasticity revealed by Einstein's insights. From clocks that tick at different rates depending on their motion to gravity's ability to bend the passage of duration itself. From theoretical wormholes and rotating universes to the paradoxes that haunt any notion of journeying into the past. And finally, to the vast gulf between what physics permits and what engineering can achieve. What have we learned? We know with certainty that forward time travel is real. It is not speculation. It is not fantasy. It is measured fact, confirmed by atomic clocks and particle accelerators, and the satellites that orbit overhead. Time passes differently depending on how fast you move and how deep you sit within a gravitational field. Every astronaut who has orbited Earth has returned infinitesimally younger than they would have been had they stayed on the ground. The effect is tiny, mere fractions of a second, but it is genuine. The universe truly permits journeys into the future. We know with less certainty what happens at the extremes. Near black holes, time dilation becomes dramatic. At velocities approaching light speed, the effect grows profound. In principle, a traveler could skip decades or centuries or millennia, arriving in a future utterly transformed from the present they left behind. The physics is clear. Only the engineering remains beyond us. And we know that backward time travel, that most tantalizing of possibilities, occupies a strange middle ground. The mathematics of general relativity permits structures that would allow journeys into the past. Wormholes, rotating universes, the exotic interiors of spinning black holes. These are valid solutions to valid equations. But whether the universe actually allows such structures to exist, whether deeper physical principles prevent their formation, remains unknown. The paradoxes that would arise from changing the past suggest that something must forbid it. Yet we cannot say with certainty what that something is. Perhaps the most remarkable insight from this exploration is not about time travel at all. It is about the nature of time itself. Our everyday experience tells us that time flows. The past is gone, receding behind us. The future has not yet arrived, waiting ahead. Only the present moment exists, a thin slice of now separating what was from what will be. This is how we experience our lives. This is how we make sense of existence. But the physics suggests something different. In the framework of relativity, there is no universal now. Different observers in relative motion disagree about which events are simultaneous. What is present for you might be past or future for someone else moving differently through space. The neat division of time into past, present, and future becomes blurred, observer-dependent, almost arbitrary. Some physicists and philosophers have drawn a striking conclusion from this. Perhaps all moments in time exist equally. Perhaps the past is not gone and the future is not unborn. Perhaps the entire history of the universe, from its earliest instance to its most distant reaches, exists as a single, unchanging structure. A block of space-time in which every event simply is timelessly present at its own location in the four-dimensional whole. This is sometimes called the block universe, or eternalism. If this view is correct, then your birth and your death and every moment between all exist with equal reality. You are always present at every instant of your life, forever embedded in the fabric of space-time. The flow of time, the sense that moments pass and are lost, might be something like an illusion generated by consciousness, a way of navigating a static structure by experiencing it sequentially. This is a strange and perhaps unsettling idea. It challenges our deepest intuitions about time and existence, but it emerges naturally from the physics we have explored. If time is truly woven together with... If different observers disagree about the order of events, then the notion of a single, objective present becomes difficult to maintain. What does this mean for the human experience of time, for memory and anticipation, for loss and hope? Perhaps it means that the moments we cherish are not truly gone. The laughter of a child now grown, the voice of someone no longer with us, the golden afternoons of summers long past. If the block universe is real, these moments still exist. They are simply located elsewhere in the structure of space-time, no longer accessible from where we stand, but not erased, not vanished, not nothing. And the future too exists, waiting at its own coordinates in the eternal block. The discoveries not yet made, the connections not yet formed, the experiences not yet lived. All of it presents somewhere in the vast architecture of time. We do not know if this view is correct. It remains one interpretation among several, a way of making sense of what the equations tell us. But it offers a perspective on time that is both humbling and strangely comforting. Every moment you have ever lived is, in some sense, still happening. Every moment you will ever live is, in some sense, already there. You are not a traveler passing through time, leaving wreckage behind you. You are a pattern woven into time itself, extended across decades, present at every point along your thread. Perhaps this is the deepest time travel of all. Not the engineering feat of racing clocks or bending gravity, but the recognition that time is not quite what we thought it was, that the river we cannot see may not be flowing at all, that past and future may be directions rather than destinations, places rather than processes. We began with the question of whether time travel is possible in our universe. The answer, it turns out, depends on what we mean by travel and what we understand about time. Forward into the future, certainly. Backward into the past, perhaps. And in the strangest sense of all, we may already be everywhere we have ever been, and everywhere we will ever be. The universe permits us to ask these questions, and that itself is remarkable. We are matter that has learned to contemplate time, patterns of atoms that wonder about their place in the structure of existence. Whatever answers await us, the asking is enough. Rest now with these questions. Let them settle gently into thought. The cosmos is patient, and time, whatever it truly is, continues its quiet way.